Welcome to today's lesson of sectoral structures theory. We're continuing to talk about symmetric structures and symmetric sets. In the last lesson, we saw that if we have a symmetric set of degree n, then it includes all the sectoral structures of degree n which are symmetric. And we defined omega of n as the size of that set. So omega of 5 is the size of the sectoral set, which includes all the symmetric sectoral structures of degree 5. Now notice that while all of these sectoral structures have degree 5, they have different orders or different lambdas. So they will include sectoral structures of orders ranging from 1 to 5. Now in today's lesson, we want to focus on certain subsets of these symmetric sets. So we want to focus on the subsets of sectoral structures that are symmetric, that have a degree n, and we will also add one more condition, and that is an order of lambda. So we saw that when we were talking about symmetric sets, we used the notation T omega of and then subscript n. Now when we're going to talk about the smaller subsets, we're going to say T omega and then subscript n comma lambda. So we are specifying it more. So for example, if we look at the set T omega subscript 4 comma 3, then we want all the sectoral structures which are symmetric, because so T indicates in this case a subset, the omega indicates symmetry, 4 is the degree, and 3 is the order. Now, while this might seem a little bit complicated, the visual ease with which we can picture these structures makes it so much easier than using some of these concepts in other forms of combinatorics. Or even we will see some applications in abstract algebra. So going back to this, we want symmetric structures of degree 4 and order 3, and there's only one such structure, and that is the structure 1, 2, 1, subscript 4. And this one looks like this. It's a semicircle divided in two, and then we have a quarter circle here and a quarter circle here. So this is the structure we are talking about. So we see that yes, it is symmetric, yes, it has degree 4, and yes, it has order 3. Now let's look at T omega 5, 3. There are two structures that fit this criteria. One of them is the sectoral structure 131 subscript 5, and the other one is the sectoral structure 212 subscript 5. Keep in mind, we are really more concerned with the geometry than with the notation. Now notice that the symmetric sectoral set T omega n is really the sum or the union of all the subsets of T omega n comma lambda, starting with lambda of 1 all the way to lambda of n. Similarly, from this, we can say that the omega of n is basically the sum of the omega n lambda, starting with lambda equal 1 to lambda equals n. For example, Let's look at omega of 5. Omega of 5 is the sum of all the functions omega 5 comma lambda, starting from lambda equals 1 to lambda equals 5. We have the theta structure. That's the only one that has a degree of 5 and, the theta 5 structure. So that has a degree of 5 and an order of 1. We have the xi 5 structure, and that one has a degree of 5 and an order of 5. There are no structures that are symmetric and have a degree 5 order 2 or degree 5 order 4. So these two don't exist. We will put zeros. And we have two structures, as we saw here, that are degree 5 and order 3. So therefore, this adds up to 1 plus 2 is 3, plus 1 is 4, and that is indeed the correct answer, as we saw in the prior lesson. So let's go a little bit broader. Let's look at, let's generate a triangle where each row is the degree of the sectoral structure, and each column is the order of the sectoral structure. So for example, let's look at this one. 1, 2, 3. So n is 3. 1, 2. Order is 0, or lambda is 0. So how many sectoral structures are symmetric, have degree of 3, and have an order or lambda of 2? There is not such a sectoral structure. So therefore, the size of that set is 0. And we will do the same for all the sets. In the book, you can see we extended it quite a bit. But here we're going to look at 1, 2, 3, 4, 5, 6. So all the way to n equals 6. And what we notice, and you can see more details in the book, Sectoral Structures Theory, but what we notice here is that this gives us, this table, or this triangle, gives us the sizes of the symmetric n lambda sets for a given degree and a given order. We notice that this triangle coincides perfectly with the Pauli-Pascal triangle. The Pauli-Pascal triangle helps us count strings that are fixed under reversal symmetry, among other things. But here we see that it also helps us count the size of the symmetric subsets for n lambda. And the way we calculate this is using what's called quantum binomials or Q binomials. So we see that instead of our regular expansion, where we have, for example, in the regular binomial expansion, n choose k is equal to n factorial over k factorial times n minus k factorial. We want to focus on the simplified version of this, which is n times n minus 1, n minus 2, all the way to n minus k plus 1 over k factorial. This is for the regular expansion. Now, when we're talking about the quantum binomial expansion, then we modify the definition. So if we say n subscript q or nq, then that simply equals 1 minus q to the n over 1 minus q. So for example, let's take a hypothetical situation here. Let's say n is 5 and q is 2. Then this would be equal to 1 minus 2 to the power of 5 over 1 minus, what was it? 2 over 2. So basically, this is how we do the quantum expansion. So if we take n q, that equals to 1 minus q to the n over 1 minus q. Notice that this is the q here. It is in both places, and n here has become an exponent. Now, if we look at the quantum binomial expansion, then we say n choose k for a q expansion is equal to 1 minus q to the n. Again, this is the q times 1 minus q to the n minus 1. As you can see, the similarity here with this expansion, all the way to 1 minus q to the n minus k plus 1, divided by, instead of the k factorial, here we have 1 minus q times 1 minus q squared times 1 minus q cubed, all the way to 1 minus q to the k. So we define this type of binomial expansion as a q expansion or a quantum expansion. Now we can define q to be a given number. So let's say q is equal to -1 in our case. So we simply replace all the q's by -1. Now let's go back and relate this to our function omega of n lambda. We say that omega of n lambda, or the size of the symmetric set, which is made up of sectoral structures of degree n and order lambda, is equal to the quantum binomial expansion n lambda, where q is equal to -1. Now notice one more thing about this expansion. If we look at omega n lambda, so let's look at this one. We will notice that it is equal to n, or omega of n minus 1 lambda. So 1, 2, 3, 1, 2, 3, so it's this one. So it is equal to this one, plus -1 to the power of n minus lambda. So what is n and lambda in this case? Let's see. 1, 2, 3, 4, 5. 1, 2, 3. So 5 minus 3 is 2. -1 to the power of 2 is 1, times omega of n minus 1 lambda minus 1, which is this one. So this is equal to this plus this. Is that correct? Yes, it is correct. Let's look at another number. Let's look at this 0 over here. We will see that this is equal to, again, this plus -1 to the n minus lambda. In this case, that will be 1, 2, 3, 4, 5 minus 2, that's 3. -1 to the power of 3 is -1, so that becomes a minus this one. So 1 minus 1 is 0. And this pattern keeps on going indefinitely. But we established this recursion, and this is exactly the recursion we see in the Pauli Pascal triangle. So what do we get from this, from these formulas or from these observations? First of all, that we have a way to calculate the size of the symmetric subsets of degree n and order lambda without having to draw the full triangle, by using quantum binomials or q binomials, where q is equal to -1. Or if we do have a row and we want to figure out the row underneath it, that's also possible using this formula here, the recursion formula. So we see that this is very similar to counting fixed points or to counting strings under reversal symmetry. And now we see that this same application works for calculating the size of these symmetric sets. Why I like this application is because here it is a very visual way to understand what we really are counting without having to be very abstract in our thought process.